Dear students, welcome back to the test compression chapter. In the previous video, we already introduced dynamic test compression. In this video, we will explain static test compression. This slide shows the difference between dynamic test compression and static test compression. For dynamic test compression, it is performed during the test pattern generation process. Every time we try to specify more bits to detect more faults, it is potentially slower but more effective than static compression. When we finish test generation and we are satisfied with the fault coverage, we can then move on to static test compression. Static test compression is done after test pattern generation. It is potentially faster but less effective than dynamic test compression. In static test compression, we consider three cases. In the first case, we perform static test compression with fault dictionary. If we don't have fault dictionary, then we can also perform static test compression with the don't care bits unfilled. In the third case, we can consider static test compression with the don't care bits filled. So there are totally three cases for static test compression. Now we start with the first case, static test compression with fault dictionary. Suppose during the test pattern generation, we perform fault simulation without fault dropping. In this way, we have a fault dictionary. In this particular example, every row represents a test pattern and every column represents a fault. In this covering table, the symbol X represents a detection. For example, T2 detects fault F5, F3, and F2. Please note that please don't get confused with the don't care bits in the test pattern. The goal of static test pattern compression is to find a set of minimum test patterns to detect all the faults. This is equivalent to a minimum set covering problem, which has been shown to be NP hard. But don't give up. There are still good algorithms to solve this problem. In 1956, when Professor McCluskey was still a PhD student, he proposed the first EDA algorithm, the Quine-McCluskey algorithm, for two-level logic synthesis. In McCluskey's algorithm, he proposed some rule to solve the minimum set covering problem. Given this covering table, we can find that there are essential faults that are detected only once. For example, F1 is essential fault because it is detected only by T4. Similarly, F3 is also an essential fault. It's detected only by T2. It is obvious that pattern T2 and T4 must be selected. They are called essential patterns because they detect the essential fault. If we select pattern T2, we can detect fault F3 and F5. If we select pattern T4, then we detect fault F1 and F4. Now we are left with only fault F2. we can either select T1 or T3 to detect F2. So the result is that we select pattern T2, T3, T4, or we can select pattern T1, T2, T4. The minimum test length is 3. This sounds a very simple algorithm. But what if there is no essential fault? What can we do? McCluskey proposed 4 simple rules to simplify the covering table. Rule number 1. We can keep only one of the equivalent rows. For example, row T1 and row T2 are equivalent rows because they have X in exactly the same columns. We can only keep row T1 and remove row T2. Rule number 2. We can remove dominated row. For example, in this table, row T3 dominates row T4 because row T3 has X in all the columns where row T4 has X, and the row T3 has 1 X where row T4 does not have X, like this column. We can remove the dominated row T4. If we select T3, we are guaranteed to detect more faults than T4. So this is unnecessary to consider row T4. Rule number 3. We can remove dominating column. Continue from the previous example. In this covering table, column F5 dominates column F4, and also F3, F2, and F1. Because column F5 has X in rows where column F4 has X, and the column F5 has at least 1 X where column F4 does not have X. So we can remove the dominating column. As long as we detect for F4, we must detect for F5. Therefore, it is not necessary to consider F4. Finally, the last rule. After the previous 3 steps, T3 is now become secondary essential, and we must select test T3, which is secondary essential pattern. After we select T3, we can detect for F2, F3, F4. We are now left with only for F1. We can either select T1 or T5. So the minimum test set is T1, T3, or T3, T5. The minimum test length is 2. Now it's time for you to practice. Given this covering table, please find which faults are essential faults, and which rows are dominated rows, which are dominating columns, and what is the minimum test length using Quine-McCluskey method. Please practice. Now, are you done yet? For question number 1, it is easy that for F1 is the essential fault, and the test T4 must be selected. After that, we can see that row T2 dominates row T3, so we can remove the dominated row T3. So the answer is T3. And for F5 dominates for F4. It also dominates F3 and F2. So we can remove the dominating column F5. Now we can select pattern T5 and T2. So the minimum test length is 3. But the answer is not unique. You can also select T1, T2, or T4. The minimum test length is still 3. Actually, we have multiple solutions to this problem. They all result in 3 test patterns. So Quine-McCluskey solved many cases in polynomial time, but not all the cases. Here is an FFT for you. We all know that minimum set covering is an NP-hard problem. So please show a special case where no rule of McCluskey's method can be applied. And what are you going to do with this special case? Please think about this interesting FFT after the video. Alternatively, if you don't want to use McCluskey's algorithm to solve this problem, it can also be solved by 0-1 integer linear programming. We can model the static test compression as a 0-1 integer linear programming problem. The objective is to minimize the number of selected test patterns, summation Ti, where Ti is equal to 1 if test I is selected. Otherwise, Ti is equal to 0. This is a binary decision variable. This programming is subject to the constraint summation Dij times Ti must be greater or equal to 1 for each fold j, where Dij is a binary constant. Dij equal to 1 if test pattern Ti detect 4Fj. For example, because T4 detects 4F1, so D41 is equal to 1. In the 0-1 linear programming, for this particular covering table, we can write the objective function as the summation of T1 plus T2 plus T3 plus T4. We want to minimize this objective function, subject to the following constraint. For 4F1, T4 must be selected. For 4F2, we can either select T1 or T3. So T1 plus T3 must be greater or equal to 1. We can do the same thing for F3, F4, and F5. So we have a total of 5 constraints. If we can solve this 0-1 ILP programming, then we can find a minimum number of test patterns. For example, one potential solution can be T1 equal to 0, T2, T3, T4 equals to 1. So the minimum number of test patterns is 3. Well, everything seems to be very good so far. It looks like this is a well-solved problem. So what's the practical issue of STC with fault dictionary? In practice, a complete fault dictionary is very large, and it is very time-consuming to perform fault simulation without fault dropping. So this complete fault dictionary is not available for large circuit. Static test compression with fault dictionary is not a scalable solution. What we need is a static test compression without dictionary. So now let's introduce more STC techniques without fault dictionary. Let's first look at the case where the don't care bits are unfilled. Suppose that we don't have dictionary, but we do have don't care bits in our test cubes. Like this. T0 is the test cube 0xx10. Please note that the x in this table means don't cares. Two test cubes are said to be compatible if there is no conflict in the specified bits. For example, T0 and the T1 are compatible. However, T3 and the T4 are not compatible because there is a conflict in one specified bit. It is obvious that compatible test cubes can be merged into one test cube. For example, T0 and T1 can be merged into 0xx10. So how are we going to find a minimum of test set by using test cube merging? One feasible solution is that we can merge T0, T1, and the T2 into one test cube, and we merge T3 and T6 into a second test cube, merge T4, T5 into a third test cube, and eventually we have T7 alone. This results in 4 test patterns. Can you find any better solution? What's more important, can we have any algorithm to solve this problem in a systematic way? We can model this problem by a compatibility graph. In the compatibility graph, the vertex Vi represents a test cube Ti. An edge Eij between vertex Vi and the Vj means that these two test cubes are compatible. For example, T0 and the T1 are compatible. So in the compatibility graph, we have an edge between vertex V0 and the V1. Adjacent vertex with edge between them can be merged into one test cube. For example, T0 and the T1 are adjacent, so they can be merged into one test cube. Now the problem becomes a minimum clique partitioning problem. A clique is a subset of vertex such that each pair of the vertex in this subset are connected. So clique is a complete subgraph. For example, in this graph, V0, V1, V2, V3 is a clique because there is an edge between every pair of the vertex in the clique. Also, V5, V6, and V7 is another clique. So, the static test compression problem becomes a minimum clique partitioning problem. In this problem, we want to partition the graph into a minimum number of cliques. For example, for this particular graph, we can partition this into 3 clicks. Click 1, 2, and 3. This corresponds to 3 test patterns. This seems to be a very good modeling of the problem. Unfortunately, minimum click partitioning problem is also an NP-hard problem that cannot be solved by polynomial time. But don't give up. There are still algorithms to solve this problem. For example, Tseng and Siewiorek is a greedy algorithm that can solve this minimum click partitioning problem. It is a greedy algorithm, and it does not guarantee optimum solution. However, most of the time, it can generate acceptable solution. The idea of Tseng and Siewiorek algorithm is very simple. Each time we select 2 adjacent vertices of maximum common neighbors. This is why it is a greedy algorithm. We merge these 2 vertices into a big super vertex. For example, V0 and V1 has 3 common neighbors. That's V2, V3, and V4. So we can merge V0 and V1 into one super vertex, which is denoted as V01. In this way, we can reduce one vertex in this iteration. In the next iteration, we merge V01 with V2. In the next iteration, we merge V5 with V6. In the next iteration, we merge V3, and eventually we merge V7. This process is repeated until there is no more edge in the graph. Then we are done. The answer is T0, T1, T2, T3 that can be merged into one test pattern. T4 is a test pattern, and T5, T6, T7 is a third test pattern. So the minimum test length is 3. Here we show the algorithm of the Tseng and Siewiorek pseudocode, where K denotes the number of iterations. Initially, it is 0. GKC is the compatibility graph in the kth iteration, and the VKC and EKC are the set of vertex and edges in the kth iteration, respectively. In this while loop, we iteratively merge one vertex at a time. First, we find a pair of vertex Vi and Vj which have the largest set of common neighbors. We want to merge Vi and Vj into one super vertex, Vs. Let n denote the set of common neighbors of Vi and Vj. So n denote the set of common neighbors in the dashed rectangle. Let S denote the union of I and j. In the next iteration, we remove vertex Vi, we remove vertex Vj, and we add a new super vertex Vs into the vertex set. And in the next iteration, we are going to build a new edge set based on the pseudocode in the red rectangle, which will be explained in our next slide. For each edge in the edge set Vn, we check if their two vertices touch either Vi or Vj. If this edge does not touch Vi nor Vj, then we keep this edge. That means if Vm and Vn are not equal to Vn, they are not equal to Vj, then we would keep this edge in the next iteration. The upward triangle here means a logic AND. For example, suppose we merge V5 and V6 in this iteration. Then the edge between V012 and V3 does not touch V5 nor V6. So this edge is kept to the next iteration. So this is what we do in the blue rectangle. In the green rectangle, we check those edges between the super vertex and the common neighbor. We insert a new edge between the common neighbor and the super vertex Vs. For example, vertex V7 is a common neighbor between V5 and the V6. So we would inject a new edge between V56 and V7. After we are done with the blue rectangle and green rectangle, we now have a new set of edges. Then we can move on to the next iteration. This process continues until there is no more edge in the set. Now it's time for you to practice. Given this set of test cubes, please draw the compatibility graph. And what is the minimum of test set using Tseng-Siewiorek Algorithm? Please pause the video and do your practice now. Now, are you ready for the answers? For the first question, we can see that T0, T1, and T2, they are all compatible to each other. But T3 is only compatible to T2. It is not compatible to T1, and it is not compatible to T0. So this is the compatibility graph. For question number 2, if we apply the Tseng-Siewiorek algorithm, we can merge a pair of vertices with the most number of common neighbors. For example, if we merge T1 and T0, we will get this graph in the first iteration. In the next iteration, we can either merge these two or these two. In that case, we will get two test patterns. So the answer is 2. Have you got it correctly? Now, again, this looks like a well-solved problem. So what's the practical issue of this method? The issue is that in practice, there are many don't cares in test cubes. Probably 90% or even 95% of test cubes I don't care. X and field test generation is typically much slower and the length is longer than X field test generation. For example, we could need 8 test cubes, but only 3 X field test patterns to test a circuit. So it is preferred that our STC start from a set of X field test patterns. So what can we do to compress the X field test patterns? So in the third case, we will introduce static test compression without dictionary starting from X field test patterns. If we have a set of X field test patterns, a very simple idea is to run reverse order force simulation. That means we force simulate the generated X field test patterns in the reverse order of ATPG. Suppose that in ATPG we generate test T1 first, then T2, then T3, and finally T4. After test generation, we would perform force simulation in reverse order, starting from T4, then T3, T2, finally T1. If we do so, we would find that for F1 and F4 have been detected by test T4. And for F2, F5 have been detected by test T3. And then we run simulation for T2 and we detect for F3. After that, we know that T1 is actually redundant. So we can choose a minimum test set of T4, T3, and T2. The advantage of this technique is that it's very simple and no dictionary is needed. Actually, it's the most popular static test compression so far. So now, here is a question. Why ATPG generated random pattern T1 at the beginning? The answer is simple. At the beginning, ATPG does not know which faults are easy and which faults are difficult. So it simply generates a test pattern for F2, which is an easy fault. And after a while, F2 is again detected by some other test pattern. So T1 would become redundant. If we can perform reverse order force simulation, of course we can also perform random order force simulation. For example, we can first simulate T4 and T2 and T1 and finally T3. In this way, we will get a test set of T4, T1, and T2. In practice, there are too many different orders to try. So, reverse order force simulation is the simplest static test compression. In summary, in this video, we have introduced 3 cases of static test compression. If we have fault dictionary, this is a minimum set covering problem. We can solve it by McCluskey method or 01 ILP. However, this method requires a very large dictionary, which is not scalable for large circuit. And the second case is compression without fault dictionary and X and field test cubes. This problem can be modeled as compatibility graph problem, which can be solved by Tseng-Siewiorek Algorithm. Finally, with X field patterns, we can use reverse order force simulation to compress the test pattern. This is the most popular and practical solution so far. Before we end this video, I want to show you an interesting photo with Professor Siewiorek on the left and Professor McCluskey in the middle and me on the right. This photo was taken in 2016 at Stanford University at Professor McCluskey's memorial event. Both me and Professor Siewiorek are students of Professor McCluskey. It is interesting that the algorithm we introduced in this lecture originated from the same academic tree. Finally, we have some FFT for you to think about. When we introduced the Tseng-Siewiorek algorithm, we said that we should keep those edges that does not touch Vi nor Vj, and we should add new edges between common neighbors and the super vertex. So how about the edge that touch only one of the super vertex but not both? For example, the edge V4, V5 is removed in the next iteration. So why is the reason? FFT number 2. We all know that minimum click partition is NP-hard problem. Please show an example when Tseng and Siewiorek algorithm failed to find an optimal solution. So this is the end of this lecture. Thank you for watching.